Hi Chem 101 students, welcome back to the third lecture on gases. This time we're going to be talking about what happens when we mix gases. And so as we've seen in the previous two lectures, the way in which we measure properties like pressure, volume, and temperature of a gas, they do not depend on the identity of gas, but simply the number of moles of gas molecules. And this has an important implication for when we mix gases. So when we mix gases, the behavior of the gases mixed together will only depend on the total sum of the moles of gas molecules, not the identity of those gases, which results in a very interesting properties that we'll talk about. Related to this is going to be the idea of what's called Dalton's law of partial pressures, where we apply a pressure to each gas in the mixture. The total pressure will simply be the sum of these pressures because every gas will contribute equally to the total pressure as proportional to the number of gas molecules that there are. Finally, we'll talk about partial pressure as a factor in solubility of gases. So Dalton's law of partial pressures says the total pressure in a mixture is the sum of the pressures of the gases in the mixture. So let's say we have two sets of gases here. So we've got a container right here, and that container has 721 millimeters mercury of helium. And then we've got a second container here that's exactly the same size, and its pressure is 432 millimeters mercury, and this is argon. Then let's say we take both of these and we put them into a new container which has the same size as the other two. And so we're putting this in here, we're also putting this in here. And so now we've taken both sets of gases and we've put them into the same container, or into a container of the same size. Now we have all those gas molecules in there. So we'll have the total pressure will simply be the sum of the two pressures. So it will be 721 plus 432 millimeters mercury. So that will be a total of 1153 millimeters mercury. And this will be for the mixture of argon and helium. And so you can see that the contribution of each of these is simply is the same regardless of the gas. To get the total pressure, we simply mix the pressures of the two gases, add the pressures of the two gases when they were separate. We add them together and we get the total pressure. And again, we can do this because each of these gas pressures contributes in proportion to how many gas molecules there are. So what this means, for example, here is that if these two containers are the same size for the helium and the argon, there are more helium atoms in this container than there are argon atoms in this container. But when we mix them, it doesn't matter what the identity of the atom is. To get the total pressure, we simply add the pressure of the two gases together. We have a kind of notation for this. If we say big P pressure with a subscript helium, that is indicating the partial pressure of helium. And so that means in this mixture, it is the part of the total pressure that is due to helium, which would be 721 millimeters mercury in this mixture. Then the partial pressure of argon here is indicated by a big P and a subscript with argon, and that is the contribution of the argon to the total pressure here, which would be 432 millimeters mercury. And again, the total pressure is from adding those two together. So here's another question that's related. The last one was talking in millimeters mercury. This one is in atmospheres, but the same idea applies. If we have a box that has 0.95 atmospheres pressure of O2, and then the same size box that has 0.35 atmospheres of N2, and then we mix those together into another box that is exactly the same size, then the total pressure will simply be the sum of the pressures of the two gases when they were separate. So the total pressure will be the 0.95 atmospheres plus 0.35 atmospheres. That is 1.30 atmospheres, and notice the sig figs here. We're adding, so we look at the place value. So these are both at the 2 after the decimal, so we make sure that we include this 0 to indicate that our last sig fig is 2 after the decimal. So notice that the units here can be either atmospheres or millimeters mercury or any other type of unit. As long as they're the same, we can add them together. Now, there's a corollary to this. These two equations that we're going to see are simply another way of expressing what we just talked about. And that is to say that if we want the partial pressure of a particular gas, well, what we do is we take the total pressure of the two gases and then we multiply it by the fraction of the molecules that are of that gas. Meaning, for example, if half the molecules or atom are one particular gas, then the partial pressure of that gas is simply half the total pressure. So we take the percentage of the mixture that is one gas and divide that by 100% to turn it into a decimal, and then we multiply that by the total pressure and we get the partial pressure that is due to this gas. So for example, let's say that the pressure was, the total pressure was 4 atmospheres, and one particular gas is going to be 50% or half, right? So this is the total pressure, and this is the percentage turned into a decimal. So we'd have 4 atmospheres times, this is just 1/2, and so our partial pressure of that gas would be 2 atmospheres, or half of the total pressure. So notice how this is just the same thing as what we saw before. If we did this for the other gas in the mixture, it would also be half, it would also be 2 atmospheres, and their two pressures would add together to make the total 4 atmospheres. So what we're saying with this equation is that if we want the partial pressure of a gas, we simply take the fraction of the total gas atoms or molecules that are that particular gas, and we multiply that by the total pressure. If that's half the molecules of this gas, then half the total pressure is due to that gas. If it's 10%, then 10% of the total pressure is due to that gas. So this is just another way of saying Dalton's law of partial pressures that we saw earlier. If we want the percentage of the gas, well, again, the pressure here that we experience from one particular gas is going to be proportional to the number of gas molecules that are in or that particular gas in the mixture. So if we want the percentage of the gas, we take the pressure that is due to that gas and we divide it by the total pressure, and then we multiply it by 100% to make it into a percentage. So for example, just using the same example we had here, if the total pressure was 2 atmospheres, or sorry, the pressure of one gas is 2 atmospheres and the total pressure is 4 atmospheres, then we get 2 over 4, which is 0.5, times 100%, which would then be 50%. So what this means is that if half of the pressure is due to one particular gas, then half of the molecules in the mixture are that gas. So another way of saying the same thing. So this is just another way of stating the same law we had before, was that if you want the pressure of total, you add up the pressure of one gas and the pressure of another, and then the pressures of all of them until you get the total pressure. And so these are just 3 different ways of expressing mathematically the same idea. And my head was kind of in the way there, but all right. So let's talk about the most common gas mixture that we are encountering every day. It is air. So air is not all one gas, it's a mixture of gases. It's about 78.1% nitrogen gas, about 20.9% oxygen gas, about 0.9% argon, and about 0.04% CO2. And then there are a lot of other trace gases, and of course there's always water, but the percentage of water depends on the humidity in the air at that moment. So this is for dry air, not including the water. So this is a related question here, and I'm going to kind of wrap this idea all the way back around to our initial Dalton's law of partial pressures. But we're asked, what is the partial pressure of nitrogen, oxygen, and argon in dry air when the total pressure is 745 millimeters mercury? That's slightly less than 1 atmosphere, so that's like a realistic type of pressure that we might have in San Bernardino. Okay, so what we do is we're going to do this for nitrogen to start. We take the total pressure and we multiply by the fraction of the molecules that are nitrogen, and then we'll get the part of the pressure that is due to just nitrogen, or the partial pressure of nitrogen as it's called. So the partial pressure of the nitrogen, N2, is going to be the total pressure times the percent of N2, and then turned into a decimal by dividing by 100%. So we take the total pressure here, we put it in right there, 745 millimeters mercury. We take the percentage of N2 and we put that in right here, so 78.1%, and then we divide by 100%. And so let's calculate this now. I'll break out the calculator here. So it's going to be 745 times 78.1 divide by 100, and we get the number 580. I'll state this to 3 sig figs, since these both have 3 sig figs. We'll say 582. And notice what happens to the percentages here. The reason why we divide by 100% is because we're trying to get rid of the percent. And so if you ever can't remember, should I divide by 100% or multiply? If you're trying to get rid of percent, you divide by percent so that you cancel the percentages. And then all we have left for units is millimeters of mercury. So our result is going to be 582, and the unit will be millimeters of mercury. And we can do the same thing for oxygen. So let's do that. If you're watching, you're probably watching on YouTube, of course, you can pause this. I encourage you to pause the lecture right now and try to do the same thing, but do it for oxygen and argon. Okay, so pause right now and try those, just like I did for nitrogen. And then after you unpause, I'll show you the result. So go ahead now. All right, so hopefully you've been able to figure out the partial pressure of oxygen and argon for yourself. We're going to do it the same way as we did for nitrogen, but we're going to do it for oxygen now. So it will be the total pressure times the percentage of oxygen over 100% to turn it into a decimal. So the total pressure here is still the same, 745 millimeters mercury. The percentage of oxygen is 20.9%. So we're going to put that right here. Divide by 100%. Now we can calculate 745 times 20.9 divide by 100. And we get 156. And notice here that our percentages, again, are going to cancel. We're trying to get rid of percent. And our unit is going to be millimeters of mercury. And so our partial pressure of oxygen will be 156 millimeters of mercury. Okay, so we've got nitrogen and oxygen. Let's do this for argon now. So that's going to be on the next slide. So our partial pressure of argon is going to be the total pressure times the percentage of argon over 100%. So we're going to plug everything in again. 740. So partial pressure of argon is 745 millimeters mercury. The total pressure times percent of argon, 0.9%, divide by 100%. Again, our percentages will cancel. We'll end up with a unit of millimeters mercury. And so now we put the numbers in, 745 times 0.9, divide by 100. And we get, we can only state this really to 1 sig fig because we have 0.9% with 1 sig fig. So we're going to say 7 millimeters mercury. Notice here the 78.1 for nitrogen had 3 sig figs. The 20.9 for oxygen had 3 sig figs. It's 0.9% for argon only has 1 sig fig. So we're going to state this result with one sig big, 7 millimeters mercury. Now, remember that the total pressure should be equal to the partial pressure of nitrogen plus the partial pressure of oxygen plus the partial pressure of argon plus the partial pressure of all the rest. But those tend to be a very, very small amount, so we can kind of ignore them. They're going to be less than 1 millimeter mercury. And so let's now turn this all the way around, and we'll state here we got for partial pressure of nitrogen 582 millimeters mercury on the last slide. We got 156 millimeters mercury for partial pressure of oxygen. And for argon, we got 7 millimeters mercury. So if we added all of these together, what is our total pressure? Well, it should be 745 millimeters mercury if we did all our calculations right? 582 plus 156 plus 7, and that is 745 millimeters mercury. The total pressure is 745 millimeters mercury. So when you add all of the pressures together, again, you get the total pressure. And this is because if we add all these percentages together, they're nearly 100%. So we've got 100% of the gases. So you can see here that when we break this down into partial pressures, what we're doing is basically the opposite of adding them up. But then we can simply, if we want the total pressure, we could add them back up again and get the total pressure. So these equations are two sides of the same coin. This is adding them up to get the total pressure. This is breaking them down by their percentages to get the partial pressure of each one. And notice that, it doesn't matter which gas it is. It only matters how much of it there is. If we want the total pressure, we just add them all up, and they're all treated the same. All it depends is how many atoms or molecules of that particular gas there are. That dictates what is the partial pressure of that gas. So we'd say air in San Bernardino has partial pressure of 582 millimeters mercury, 156 millimeters mercury, and 7 millimeters mercury for argon. We just figured that out. And of course, the air pressure will change all the time, the barometric pressure, but this is a good representation of the partial pressures of each of these gases in San Bernardino. So now we can go the other way too, and if we did not have the percentage of nitrogen, we could figure it out. What we do is we take the partial pressure here of nitrogen, we divide it by the total pressure, and that gives us the fraction of molecules that should be nitrogen. Then we multiply by 100% to make it a percentage. So as we saw earlier, the total pressure is the pressure of nitrogen, oxygen, argon, and the rest. So we add them all together and we get 745. We did that on the last slide. So if we want the partial pressure of nitrogen, we take, the percentage of nitrogen, we take the pressure that is due to nitrogen, 582 millimeters, and then divide it by the total pressure times 100%. So for the partial pressure of nitrogen, we plug in 582 millimeters mercury. For nitrogen, we plug in, or for total pressure, we plug in 745 millimeters mercury. And then we multiply by 100%. That will turn this from a decimal into a percentage. So let's do that. 582 divided by 745 times 100 equals. And we get 78.1%. Notice here for units, millimeters mercury cancel, and the unit we have left here is percent. We treat percent just like a unit. So if you ever forget, if you don't have percentages and you want to turn a number into a percent, you multiply by 100%. That adds on the percent there. And we get that the percent of nitrogen is 78.1%, which is what we were given before. And so again, all these three equations that we've seen are basically three equations that are describing the same idea. Which one you use just depends on what you're trying to find. If you want to find the percentage, then you take the pressure of that gas over the total pressure, giving you the fraction of gas molecules that are due to that gas, and then you multiply it by 100% to turn it from a fraction into a percentage. If you want the total pressure, you add up the partial pressures of everything. And if you want the partial pressure, you take the percentage, turn it into a decimal, and multiply that by the total percentage, or total pressure rather, just like we had on the last slide here, like this. So if you want the partial pressure of one gas, you take its percentage, turn it into a decimal, and multiply it by the total pressure. And so that's Dalton's law of partial pressures. And that's how you can figure out the pressure due to each particular gas. So why, let's say some of you are scientists, so of course you're going to care about the pressure of gases, because lots of chemical reactions and scientific investigations are regarding gases, and you'll need to understand how they behave. If you're going to be someone in the healthcare sciences, well, why would you care about this? You would, because the way that we breathe air depends all on these gas laws. So, for example, when we want to breathe in, we don't suck in air per se. What happens is that we have a muscle, the diaphragm, that increases the volume of our lungs, which decreases the pressure inside, and so the greater pressure air will rush in to fill in that space and equalize the pressure. And the reason why gas mixtures are important is because our body is used to breathing a certain partial pressure of oxygen. And for whatever reason that partial pressure isn't right, or the partial pressure of other gases like nitrogen isn't right, that can cause problems for a person's body. If they stop breathing, for example, or they're breathing too quickly, or if they're diving. So the pressures of gas mixtures are super important for divers. Anyone who's diving underneath the water needs to be very careful about the partial pressures of the gases that they're breathing. And if you're working in a hospital on the coast, they're going to have special measures to help someone that has had problems with their diving. And we'll talk about those. So let's say we're scuba diving. Before we go underneath the water, the total pressure on the diver is 1 atmosphere at sea level, the air pressure. But as you go underneath the water, you've also got the pressure of the water pushing down on you and against your chest. And that pressure will increase by 1 atmosphere for every 32 feet that someone goes below the surface of the water. So at sea level, it's 1 atmosphere. For 32 feet below sea level, the pressure is 2 atmospheres, and another 32 feet down, it's 3 atmospheres, and so on. So we just calculated what the partial pressure of nitrogen is when the total pressure was 745 millimeters mercury. Let's do it for when the total pressure is 1 atmosphere, for when we're at sea level. So what is the partial pressure of nitrogen and so what is the partial pressure when it's 1 atmosphere? And then here, what if we go beneath the surface? What is the partial pressure when we go 32 feet below the surface and the total pressure is 2 atmospheres? We're going to calculate both of these. And why would the diver be worried about the partial pressure of nitrogen? Let's take a look. The answer is here. So the partial pressure of nitrogen at sea level, when the total pressure is 1 atmosphere, will be that pressure, the total pressure 1 atmosphere, times the percentage of the air, which is nitrogen. And if we're breathing normal air, we saw that was 78.1%, divided by 100% to turn it into a decimal. And so our percentages cancel here, and we're going to have units of atmospheres. And so we do 1 times 78.1 divided by 100. And so we get 0.781 atmospheres, or our partial pressure of nitrogen. So that is at sea level, okay? But if we go down 32 feet below the surface, although the percentage of nitrogen is the same if we're breathing normal air, the total pressure now is going to be 2 atmospheres if we're 32 feet below the surface of the water. Even if the percentage of nitrogen is the same as regular air, so it's 78.1%, now the partial pressure of nitrogen from the tank, the high pressurized tank that you're breathing, is going to be 2 atmospheres, since that's what's pushing against your chest. And we're going to have a new partial pressure of nitrogen. And so that partial pressure will be 2 atmospheres times 78.1% divided by 100%. And so we get 1.56, or 1.6 if we're going to 2 sig figs, because 2.0 has 2 sig figs. So we'd say 1.6, and again, our units are going to be atmospheres because percent will cancel, we'll end up with atmospheres. So this is going to be 1.56 or 1.6 atmospheres at 32 feet below the surface. So as you're diving, if you're a diver breathing normal air that is 78.1% oxygen, as you're diving further and further below the surface, the partial pressure of the nitrogen that you're breathing is going to be much greater than it would normally be if you're just breathing water, breathing air rather, at 1 atmosphere total pressure. And that is a problem, because what happens is if you're breathing a higher partial pressure of nitrogen, then you'll have a greater amount of nitrogen dissolved in your blood. So the higher the pressure of the gas, the more of that gas will dissolve in the diver's bodily fluids like their blood. And one problem is that if the concentration of nitrogen is too high in the blood, this could lead to a narcotic effect. And so it would be very bad for a diver to actually be breathing a very high partial pressure of nitrogen, because the body is not used to that, and it can result in the diver getting confused and getting stuck under the water and perhaps dying. And so it's very important that the way that the diver has gases in their tank that they're breathing, and the way that they approach their diving, it makes sure that they're not breathing such a large partial pressure of nitrogen. Another issue is that, let's say the diver has to rapidly go back to the surface, and they have a large amount of nitrogen, larger than normal, dissolved in their blood. So they quickly rise to the surface, and suddenly now the pressure of the air they're breathing is no longer 2 atmospheres, it's 1 atmosphere again. And so the higher amount of nitrogen that is in the blood now will be trying to escape to return to a normal amount of nitrogen. So when the pressure is suddenly removed, the nitrogen is no longer soluble in the blood, and so it comes out very quickly. And so it's basically like leaking out through all, trying to escape from all the little places it can in your body. And this becomes a very painful thing, a condition known as the bends. And so if a diver has this problem, they can be treated at the hospital. So in Long Beach or anywhere along the coast, they'll have what's known as a hyperbaric chamber. So hyper standing for more, and baric meaning pressure. So a chamber that is higher in pressure than normal atmospheric pressure. That way they can, instead of quickly lowering the pressure so that all the nitrogen wants to come out of the bloodstream, the pressure will be slowly lowered so that the nitrogen can slowly and more naturally be breathed out without it bubbling up out of the fluids and causing this painful bends condition. So if you're a diver, you need to be aware of your depth, and you also need to be aware of the gas mixture that you're breathing, which in actuality, for the reason we just discussed, is not usually regular air. It is not 78.1% nitrogen, because as we saw, that just results in too high of a partial pressure of nitrogen, and that can result in the narcotic effect if too much nitrogen is dissolved, or the bends if the diver has to quickly resurface. Now, if you're a healthcare practitioner, why else would you care about gas laws and gas mixtures? Well, it's because we breathe a gas mixture that is partially oxygen, and it's the oxygen portion that we require to continue living. We actually have to have a constant stream of oxygen coming into our bloodstream. If we don't within less than 10 minutes, we will certainly die. So let's say someone cannot breathe for various reasons. How is it that we can treat them using our knowledge of gas laws to make sure that the concentration of oxygen in their blood is remaining high enough. So we will perform respiratory therapy, and this involves the principles of the gas laws here. So the primary goal of a respiratory therapy when someone is not getting an oxygen is to increase the partial pressure of oxygen so that there's a greater dissolved oxygen in their blood. And there are two ways that we can increase the partial pressure of oxygen. Number one, we could pump them air with a higher total pressure. So if we increase the total pressure of air that they are receiving, they will have a higher partial pressure of oxygen, and thus more oxygen will dissolve in their blood. The way we do this generally is if someone has stopped breathing, we perform rescue breathing. And so we using a device that pumps air into the lungs or some mouth to mouth, someone will pump a greater pressure, total pressure of air into the lungs, and that will result in a greater partial pressure of oxygen. So in this situation, we're using normal air, which is 20.9% oxygen, but we are pumping a higher pressure of air into the lungs. So if someone is just normally breathing oxygen, the partial pressure of oxygen would be the total pressure, which for normal breathing would be 1 atmosphere, times the percentage of oxygen over 100%. So at normal pressure, this total pressure will be just the normal 1 atmosphere or so. And so the partial pressure of oxygen will be the 1 atmosphere times the 20.9% over 100%. Again, our percentages here will cancel, and we'll end up with units of atmospheres. Okay, and so we calculate that out. 1 times 20.9 divided by 100. You could probably figure this out without a calculator, but it's 0.209 atmospheres, or 0.21 if we're going to 2 sig figs here, because the 1.0 has 2 sig figs. So that is the partial pressure of oxygen that we're normally breathing. But if we're performing rescue breathing on a patient that stopped breathing, we're going to pump into their lungs a forced air at a higher pressure, let's say 1.5 atmospheres. So now the partial pressure of oxygen will be different because the total pressure will be different. Instead of 1 atmospheres, now the total pressure is 1.5 atmospheres because we're forcing a higher pressure of air in their lungs. Now we're still just forcing air, so the percentage of oxygen is the same. It's 20.9%, and we convert that to a decimal by dividing by 100%. Again, our percentages cancel. We have units of atmospheres. So now it will be 1.5 times 20.9 divided by 100. And so our new partial pressure of oxygen with the higher total pressure will be 0.31 atmospheres. And so by forcing the air into the lungs, we have now provided the patient with a higher partial pressure of oxygen, which means a greater amount of oxygen should be able to dissolve in their blood, and that will result in an increase in their blood oxygen percentage, and that could save their life. So that's one strategy that is used, particularly when someone with normal healthy lungs has stopped breathing for some reason. The other way in which respiratory therapy is provided is by providing a enriched oxygen mixture. So this is for someone often that their lungs are having trouble absorbing the oxygen. We'll often give them an oxygen tank, which will have usually not pure oxygen, but will have an enriched gas mixture that has a greater percentage of oxygen and a lesser percentage of nitrogen compared to regular air. So again, the partial pressure of oxygen will be the total pressure, which is now going to be 1 atmosphere. So whether we're breathing through the tank with just a kind of tube in the nose, it's not forcing the air in, so you're breathing it at a normal pressure, about 1 atmosphere. Or we're breathing air at 1 atmosphere. Our total pressure is going to be 1 atmosphere. But the percentage will be different. So for the higher percentage gas mixture, we'll have a greater percentage of oxygen here. So again, if we're breathing normal air we'll have a total pressure of 1 atmosphere, and for normal air, the percentage of oxygen will be 20.9%. So just like before, we're talking about a partial pressure of oxygen of 0.21 atmospheres. However, if we give someone the oxygen tank with a greater percentage of O2, we'll have still a total pressure of 1 atmosphere, because it will just be kind of leaking throughout the tank slowly into the tubes that are inserted into the nose. But the percentage of the oxygen that they're breathing will be greater. It will be 40%, let's say, instead. And so now the partial pressure will be 1 times 40 divided by 100, which of course will be 0.4 or 0.40 to 2 sig figs. And so now that's the other way we can have the patient be breathing a higher percentage of oxygen. So we can either force regular air into their lungs at 20.9% at a higher total pressure, or we can have normal atmospheric pressure but a higher percentage of oxygen. Both of those ways will increase the partial pressure of the oxygen that the patient is breathing, and will thus increase the absorption of oxygen into the bloodstream. So as we've been talking about, a higher partial pressure of gases results in a greater solubility into the liquid, like the bloodstream. This is true for other liquids too, like water. So one, probably the most familiar to you of gases dissolved in liquids is CO2 dissolved in soda water. So when you have soda being canned, it's going to be closed up, and in the top above the liquid, there's going to be a high percentage of CO2, like maybe 90%. But then you go psh, and you open it up, and now that high percentage of CO2 has now been released, and that soda is now exposed to normal air, which only has 0.04% CO2. So what that's going to do is that's going to result in a decreased solubility of the CO2 in the water. And so you'll find that over time your soda gets flat, because it no longer has the high partial pressure of CO2 above it, so the solubility of the CO2 in the water is decreased. When you pop it, you change the partial pressure of CO2 above the liquid from 90% down to 0.04%. And the result is that the CO2 is less soluble. Assuming we have a total pressure of 1 atmosphere here, we bottle the soda with 90% CO2. So if we're calculating the partial pressure of the CO2 above the soda, it's going to be the 1 atmosphere total pressure, but times 90% CO2, turn it to a decimal. And so our partial pressure of CO2 is 1 times 90 divided by 100. That's 0.9 atmospheres. So when the soda is closed, you have 0.9 atmospheres of partial pressure of CO2 above the liquid. And so the CO2 does stay dissolved in that case. However, once you open the soda, now the partial pressure of CO2 above the soda is going to be the same as in the air, or the percentage rather, 0.04%. So if we calculate the partial pressure of the CO2 now, it's going to be the total air pressure, about 1 atmospheres, times the percentage of CO2, now 0.04%, divided by 100%. And so now we have 1 times 0.04 divided by 100, and we get 0.0004. So once the soda has been opened, the partial pressure of CO2 above the soda is 0.0004 atmospheres, much, much lower. And so for that reason, the CO2 is much less soluble in the water, and so the soda will slowly get flat over time. So much less CO2 will dissolve, the bubbles will form in the liquid, and the gas will escape. One last idea that we'll talk about here very briefly is the idea of gas diffusion. And so this is the speed at which gas molecules can move from one place to another. So we've been using the temperature Kelvin as a proxy for molecular speed. To be more exact, the temperature is actually a measure proportional to the kinetic energy of the molecules. And so what this means is that if the molecule is very heavy, by the way, kinetic energy in physics is expressed as 1/2 mass times velocity squared. And so what this means is that although these have the molecules will have the same energy, if it's a light molecule that has a low mass, its velocity will be higher even at the same kinetic energy or the same temperature. Whereas for a bigger molecule that's heavier with a greater mass, its average kinetic energy will be the same if it's at the same temperature, but its speed will be smaller. So the way we can evaluate the relative speeds of molecules is we can say, okay, which of these gas molecules, helium, neon, argon, or krypton, will move the fastest at the same temperature? So they're all the same temperature. So that means, same temp, that means that they have the same kinetic energy. But what that means is that for small molecules, or light molecules rather, like helium, that means they will be moving faster than the heavier ones. So you can think of kinetic energy like the energy of movement. Like imagine that you're playing football or something, and you got to tackle someone, you got to hit them and knock them over. So if you have a really light guy, that light guy is going to be going a lot faster, or going to have to go a lot faster to knock someone over. Because the guy's light, right? But if you have a heavy guy, even at a slower speed, that heavy guy will have enough energy to knock the person over. That's kinetic energy. And so what this means is that they're at the same temperature, they have the same kinetic energy, but that means the lighter molecules or lighter atoms are moving faster than the slower atoms that are at the same temperature. The helium here will move the fastest because they're all at the same temperature, they all have the same kinetic energy, but the helium is the lightest at 4 grams per mole versus neon, which is 20 grams per mole, argon, which is 40 grams per mole, and krypton, which is 84 grams per mole. So if they're at the same energy, the heavy molecular atom is moving more slowly, and the lighter molecular atom is moving faster. And so that's related to diffusion. This is also related to filling up car tires, for example. Some car dealerships will offer argon to fill your tire, or some tire shops, as opposed to regular air, which is mostly nitrogen. And the reason why is because the argon has the molar mass of 40 grams per mole, whereas the nitrogen has a molar mass of 28 grams per mole. So the nitrogen molecules are moving faster than the argon molecules when they're at the same temperature because they're lighter. And so the result is that the nitrogen molecules will be able to find places to escape the tire a bit faster than the argon. And the result is that the argon tires will stay inflated slightly longer. That said, it's probably not worth the difference. Some tire shops offer nitrogen, actually, which is very strange. So the problem with offering pure nitrogen is that is actually inferior to air, because air has some oxygen in it, which has a molar mass of 32 grams per mole. But they claim that the superiority of the nitrogen is due to the fact that the oxygen is corrosive to the tire material and the rim material. But I am heavily skeptical of that. I would never pay additional money to have nitrogen in my tires. I might consider pure nitrogen. I'd just get regular air. I might consider argon, because there is an argument that I would not have to fill up my tires as soon. But even then, I don't think it would be worth that much to me. But that's just the idea here, that at the same temperature, heavier molecules move slower on average than lighter molecules, and that is diffusion. And that is the end of the gas laws chapter. So we have discussed the various gas laws, including the combined gas law, the ideal gas law, standard temperature and pressure, and also Dalton's law of partial pressures as with respect to mixtures of gases. And so I look forward to seeing you guys in office hours, and good luck on your homework and quiz this week. Have a good one.